As I said, we're now finally ready to plot our LOPs for each of our problems. So we're going to start with the 18th of August problem up here. And we're going to use the information that we've been calculating to actually find our LOP. So right here are the four pieces that we plot with. Our latitude, longitude, ZN, and intercept. So we're going to first just place down our latitude and our longitude to mark our assumed position. Now, luckily, part of what is so advantageous about rounding to the nearest degree for the latitude is we don't have to measure our latitude. Our assumed latitude is along this line. It's along the 19 degrees north parallel because we picked for it to be there. Makes it a little bit easier to put down the assumed position because now we only need to worry about our assumed longitude, which is 108 degrees, 7 minutes west. So if we come back to the chart, we just have to plot a point that is 108 degrees, 7 minutes west on this parallel here. You can see the 108 degree meridian is right there. So now we just need to measure 7.8 minutes away from this to the west. So we come to our longitude scale and we measure 7.8. Now this is not accurate enough to get 7.8, but you can get, you can just say a little bit less than 8 minutes. So here's our, zoom in more. Here's our 0 mark. Here's 10 minutes, 6 minutes. So here's 8. So if we go a tiny bit less than 8, we've got just about 7.8 on our correct scale. So we bring it over to the 0.8 meridian, or the 108 meridian, sorry. We mark it along the line till we get there. We just draw a little tick mark. It doesn't need to be anything special. And we can say that right there is our assumed position of 19 degrees north, 108 degrees, 7.8 minutes west. And we know that that is the point that this massive calculation here that technically requires the whole, like a quarter of the circumference of the Earth, it passes through that point exactly. That is our AP right there. So now next we have to plot our azimuth. And our azimuth was, if I can pull up the page, our azimuth for the 18th of August problem is 100.4 degrees, true. So again, you can't get 0.4, but we can just do 0.5. So we're going to plot a line, a bearing of 100.4 degrees off of that point. So we come down here, we set our triangle with the window passing straight through the meridian. We get 100 and a little, and just about halfway between 100 and 101. That's our correct angle. And then we move it into position so it's just passing through our assumed position. Now it's in the right spot. Now we need to remember direction. 100 is this way, but you want to draw it in both directions so that you can remember which way is towards and which way is true. And you want to clearly identify which is which. So what I usually do, what I was taught to do, is draw a solid line in the towards direction and a dotted line in the away direction. And you can make it decently large. And then I usually end it with an arrow on the towards side, though that's not necessary. You'll see really skilled guys, they'll just plot it, put the other triangle right there, perpendicular, measure the distance of the intercept, and then draw it immediately. You don't need to do it that fancy. Just get your point, draw your azimuth in the towards direction, and a dashed line in the opposite direction, in the away direction. That way, either way, you can have your, you can plot either away or towards, depending on what it is. You don't need to remember that in this problem it's away. So now we've got an intercept of 0.2 minutes away. All right, where did I put my dividers? Here they are. 0.2 minutes is 0.2 miles. That is basically nothing. I mean, I can't measure 0.2. You know, that's a mile right there. So 1/5 of that, it's within a width of a pencil. So you can honestly just set it right at the assumed position. But remember, the purpose of the intercept, if we're now saying that this is essentially the intercept, the purpose of that is to place a line perpendicular to the azimuth. So you take your azimuth line, you line up your triangle. Remember, this line through the center here, this 0, 9, 0 line, you can use to get perpendicular lines. You line it up with your azimuth. I'm going to put it in position. I'm going to put it like a hair forward of the actual assumed position, so we're like kind of 0.2 nautical miles towards. Oh wait, we were away. 0.2 nautical miles away, which this is the away side, so we move it a little bit that way. And now you draw a nice long line. Technically, it should go like 3 inches to either side of the track. So it should be at least 3 inches on this side and at least 3 inches on that side. And that right there is your LOP. Now it needs to be labeled. So you're going to come to the top here, and the correct way to label it is you draw the symbol for the sun, because we're working with the sun here. You make it the lower limb, because we were doing the lower limb, and you write the time, which this shot was taken at 10:36. So now anyone can come in and they can look at the chart and they can see, oh, we had a 10:36 sun shot that got us this line of position here. And if you compare that to our DR position, you see that we're at several miles, I mean, assuming that we're at the point where the LOP intersects with the track line, which we might not be, we don't know that. But if we were, we'd be several miles ahead of our track. Doesn't mean you did anything wrong, it might mean the ship is off course. It could also mean that we're over here, and we're not necessarily ahead of track, but we're a little to the east of the track line, whatever it may be. Technically, it's equally mathematically likely that we're up here, but we're probably over here. So that's how you set down your LOP. We're going to go to the next problem. I have on this side of the paper. This is the 4th of June problem. So we've got our track line already set up. Step 1, we've got to place down our assumed position. So for this one, our assumed latitude was 27 degrees south. So there's 27 degrees south. And 122, 16.1 minutes west. So this meridian is 122 degrees west. So we're going to go 16.1 miles, or 16.1 minutes, sorry, further west than that. So we place one prong on the 10 and one prong on the 6. So here's 2, 4, 6. Remember, we're technically 16.1, but it doesn't matter. There's no way to measure that properly. So we come 16.1 minutes west of 122 degrees. Place down our assumed position. There we go. That's our assumed position for our calculations. Now we plot our azimuth, which was 44.2 degrees true. So we take our triangle, we measure 44.2 degrees, which you can do is just a little more than 44 degrees. Right there. Remember, 44 is this way. So this is our solid line for towards and our dashed line for away, because we might not remember whether we've got towards or away for this problem. Draw the arrow in the front. And then finally, our intercept is 44.9 minutes towards. So basic 44.9, we'll do 45. 45 minutes, which is 45 miles. So we measure on the latitude scale 45 minutes of arc, right there. Place that on our assumed position, mark where it passes through our azimuth, and now we'll set a perpendicular line right there. Have it about 3 inches to either side of the track line. There we go. And we label that lower limb of the sun at 0915. There, and there's our LOP for the second problem. And you can see in this case, we're a couple miles behind the track line because the track is going this way. But we're still pretty close. So this difference in distance here could again be the ship just genuinely being a little bit behind schedule. So now we need our third problem, which I believe is here. Yeah, here's the 21st of November. And this problem, I set up the plotting sheet upside down because again, if you're in the south, you could either have it right side up and then just have the numbers go down, or you could flip it over completely and have the numbers go down again. This way you can kind of visually tell that you're in the south. Now that we've got that ready, come to our third problem. Here, assume latitude 23 degrees south. We've got that right here as our central latitude. And by the way, the reason we keep lucking out and getting our central latitude and longitude is right around where the assumed position is, that's just good planning in advance for where you set your starting position. When you set up the page, it's up to you on how far ahead you want to think to set this up well, so it will land in the center of the sheet. But 23 degrees south and 78 degrees 26.3 minutes east. So here's 78 degrees. So now we just need 26.3 minutes east of that. So we come up to the longitude scale. 20, 2, 4, 6.3 is a minuscule amount. That's about it. We measure it going east from our meridian. Sorry, there's a alarm sounds distracting me. East from our meridian. There's our assumed position. Now we plot our azimuth of 095.8. So we take our triangle, and if you're good at planning ahead, you can see that this is already going to get us really close to our DR position. Measure out. Here's 095. 0.8 is really close to 096. So that's about right. There we go. 95 is this way. So we draw a solid line this way and a dashed line this way. And different mates, different professors like different setups for how your azimuth line should look. Some want it just a solid line all the way through. Some want it like invisible where you erase it afterwards. It's up to them what they want, but this is what I was taught. So here's our azimuth. And now, finally, lost the page again. We get our intercept of 6.6 minutes true. So we measure out 6.6 miles. So here's 5 miles. We'll zoom in so you can see better. Sorry. 6, a little more than half, 0.6, gets us right there. So we mark that point, and we draw our perpendicular line off of that. About 3 inches on either side, and we label it lower limb of the sun at 0816. There you go. And so that, in summary, is the full process of getting a line of position on a universal plotting sheet, starting all the way from having your piece of, actually from setting up the plotting sheet, getting it ready to work off of, setting it to the correct latitude, and getting your DR position for around the time you're taking your shot, to going over to your nautical almanac, calculating your GHA, your declination, correcting your GHA to LHA, getting all your, what else? Getting your assumed latitude, which is easy. Then going to the pub 229, correlating your LHA, your latitude, your declination to get your HC and your ZN, and interpolating to get them more accurate. Then going back to the nautical almanac to clean up your shot from HS to HA to HO. Finally, compare your HO to your HC to get your intercept. And then once you've recorded your assumed latitude, your assumed longitude, your azimuth, and your intercept, then you plot the assumed position, plot your azimuth, move your intercept along the azimuth, and then get your perpendicular line, which is your LOP, which is your true position in each of these problems. It's a long process, and there's a lot of moving parts. There's a lot of things you need to remember. Do apply in this case, but don't apply in that case, especially because we haven't even gotten to stars and planets yet. But ultimately, this is how you accomplish this. For one LOP, you need 2 more to actually get a fix, and that's what we're going to do next.